Hello, everyone. So this is a talk about some of the work funded by DOE, and it's actually a work not directly related to the project, but during the process we find out something very interesting, and we would like to report to the community. We use this as a chance to asking for help, then solving problems. If we look at the nuclear power plant right now in the United States, many of the nuclear power plant has been more than 30 years old, and then some of them it's in a very complicated environment. For example, if you go to any nuclear power plant environment, the workspace it's pretty dense, and then a lot of those pipes and then valves are located very close to each other. And in the control room, there are so many buttons, so many lights, and so many gauges to show the data about the operation. And then it's like a very complicated car, and then people need to know how to drive it. And then if we have autonomous car driving, and then we think in the future we should have kind of like autonomous driving for nuclear power plant, and if that's possible. And then AI is the term we could say, okay, AI could also drive this complicated system. So for civil infrastructure domain, the energy infrastructure is a very important one. And then during the past 30 years, many of those nuclear power plants across the world has been getting old. And then getting old means there are a lot of those small problems, and then they usually cause shutdowns. And then shutdown means that there is an unplanned downtimes, and then the failure of those here and there of the system cause problems. And then those kind of downtime is very expensive. For example, in India, one of the nuclear power plant has been getting old, and then the downtime each time is going to be $250,000 per day. And then each of the maintenance could be thousands, tens of thousands of dollars. And the people say, okay, if we want to have some kind of technology to help us to predict or to understand which part of the nuclear power plant has problem, then we need to have a system called anomaly detection. Anomaly detection could be a domain, a field, artificial intelligence and machine learning could help. But I would show you that anomaly detection itself is not sufficient. Let's take a look at this anomaly detection problem. Anomaly detection means it's a deviation from an acceptable range of the observable variable. For example, if you have many sensors putting in the nuclear power plant for monitoring the condition, like a flow, temperature, of all kinds of instruments, then the anomaly would be the parameter outside of the predefined range, or a combination of multiple sensors readings is like looking weird. It's weird. For example, certain things should going up and certain things will going down. And then if that combination happens, it's not normal, even though everything is in the predefined range. Then correlated pattern recognition from multiple sensors readings is something needed for people to understand it's normal or abnormal. It's not just we see this is out of the range, and a range is just one single value. A combination is even more important. And then there are so many sensors inside the nuclear power plant right now for monitoring the condition of all kinds of mechanical systems. For example, I listed a few of these here, and the losing parts monitoring, and the fatigue monitoring of the material, leakage monitoring, vibration monitoring. And then each of these have certain sensors. And sometimes the simultaneous monitoring of multiple anomalies is necessary because, as I said before, it's not just one single parameter guardian problem. It's a combination of those parameters combined together. It's a problem. So some people try to say, let's have artificial intelligence and then to detecting all those anomalies. And actually, some companies put a lot of resources to solve those kind of problems for monitoring the condition of a nuclear power plant. And then they have analysis engine using all kinds of artificial intelligence algorithm, clustering, PCA. That I'm not the major of machine learning and artificial intelligence. I'm a civil engineer, but I heard about those terms, and then I realized that, okay, artificial intelligence is very useful. Let's see how it works. And then right now, the process is like this. We have the real-time operation data, and put into the analysis engine, whatever algorithm they're using, and then they are going to output a risk level. And the low risk will be normal, and the high risk will be abnormal. And then the classification algorithm could also provide more details to help the domain expert to find out what is exactly behind those anomalies. And then behind those engine, it's a historical operation data. And then a lot of those algorithms from artificial intelligence domain. And then let's see how it works. Actually, there's two cases I would like to show you. One of the algorithm could show that the temperature increase of the turbine shows that the cooling system might have a problem. But actually, after based on the historical reporting, and then the expert look at the reported anomaly, they'll find out it's not the cooling system has a problem. It's actually the damage of the valve, and the valve getting the water out. Even though we got enough water in, but the valve has the problem, and then the too much water getting out, and then the cooling system does not get enough water. It's not the problem of the cooling system, it's the problem of the valve. And then that problem, the system will not be able to tell us it's the valve's problem. It's actually a combination of the problem. It's input, it's okay, but output is not, the sensor is not okay. Another case, it's in this case, it's also a valve problem, and then the input, it's okay for the temperature balancing system. This temperature balancing system has a valve also, and then sometimes if there is extra heat, then the system will be automatically activated by the artificial intelligence system, and then somehow the valve does not work, and then the system get activated automatically because of the valve is not working. Then so in that case, it's people need to repair not the system itself. They need to repair the valve. But all of those things should go through the expert investigation. AI will not be able to tell the valve has the problem. They're just going to say, okay, there is something wrong, but I don't know what. Then I would show some challenges and then pose the questions to our AI experts, and then to see maybe we could work together and help the nuclear industry as a team. Number one, we have this data collection challenge. So the operational data, it's not just the data, it's a lot of those kind of data from multiple sensors. And then the problem is some sensors might be damaged. And then right now, the model we are using only consider single sensor, and it's very, very limited amount of consideration about the combination of sensor showing like abnormal combination pattern for indicating the nuclear power plant as a problem. And the data quality is a problem, but data processing is also a problem. Data processing means in the environmental condition, there are so much noise. And then if we have some abnormal signal, and then that signal is so weak, and it's overwhelmed by the noise. And then sometimes there is no baseline. We're not going to say what is normal, what is abnormal. There is no baseline, there's no label. And then if we want to tell someone is normal or abnormal, then we have no baseline. That's very, very difficult. And then maybe someone already know the solution, but I would bring that as a question. Number three, interpretation. And I would say explainable AI might be challenging for us in this case, because there are so many parameters, and it's very, very hard to use some of those algorithms right now to derive what's the causal relationship between the control parameter and then the abnormal we observe. And then data interpretation is a big challenge. The research question I pose here is, one, how to check and enhance the data quality and enhance the data fidelity. Number two, how to classify anomalies from noisy data without any baseline. Number three, how to extract a causal relationship to help us to make a meaningful control of the nuclear power plant.
Cool.
And then,
well, for this very nice talk, and sorry for the interruption due to the time limits that we have. And
yes, I'm concluding right now. Yes. Sorry, can you? Yeah, this is the last slide. Yeah.
Cool.
Yes. Yeah. So this is like a big picture. I would say it's more like a integration of AI and human intelligence, and then the digital twins used by the industry right now for anomaly detection and interpretation. If we could do that, we should be able to not only detecting anomaly, but we also explain the anomaly and then try to help people to get information out of those anomalies. That's it. Thank you.
Great. Thanks a lot. And again, as we see already in the chat box, if you have questions, feel free to ask in the chat box, or you can stay at the handout session at the end of the day, and then we have more discussion time. And let's thank Pingbo again for the very interesting talk, and that raises a lot of research questions that leads to potential collaboration opportunities. Thank you all.
Sure, thanks.
Cool.